I think St. Martin's the island that's divided half French and half St. Martin and St. Martin, depending on whether it's the Dutch or the French half. And so the interesting thing that links to fluid mechanics, I guess, for this is that big planes come on a small island, and the runway and the road that circles the runway between the runway and the sea is pretty close to the fence. And I guess that says it all. But that's I don't know why people go out there to, well, you'll see, to experience the jet blast and probably get sandblasted as well, as imagine. So it's kind of a corollary of the San Francisco blowing the truck off the taxiway kind of deal. So it's just a little bit of humor for the morning. I can't believe you haven't seen this. You must be YouTube aficionados, aren't you? So anyway, so they're all little microcosms of velocity squared coming out of the engine, killing on them as they lie on the sand, and changing to the pressure that's exerted on them. So fine. So you know how that works. Yeah, so interesting. Yeah, interesting thing to see, I guess, in some respects. So it's one. What else? What did I do? Something more scientific for us, I guess, is this. This is kind of. I'll play this a few times. So we've been talking about conservation equations, and maybe we'll probably look at this today. You know, if you're working in fluid flow and porous media, so certainly for petroleum engineers, environmental systems engineers, energy engineers, if you're looking at geothermal energy. Whoops, I don't want to do that. I guess I can't put it so it loops, I don't think. Or perhaps I could if I figured it far enough. So we use conservation of mass and conservation of energy that we're talking about this week, to be able to write the equations for flow and porous media. And so this is kind of an interesting thing. Actually, a colleague of mine, his name's Rami Grader, was a fellow professor in our department, and he went away 10 years ago as chief scientific officer for Ingrain. So Ingrain are an interesting company. The innovation was that you take the drill chips that come out of the drill holes. So you have tiny little chips that would be for shales, and so you X-ray CT them to see where the porosity is. And so you can see these kind of shadowy spherical grains in this. So you can build up an architectural digital twin, I guess you'd call it in these days, of what the pore space looked like. And then you run a model to be able to predict exactly how fluids would flow through that. And from that prediction, by putting a pressure upstream and downstream and measuring the flow rate through it, you can get an idea of Darcy's law, which we'll talk about, which is really just the law that says what the resistance is, the frictional resistance is to flow within porous media. So a high permeability medium is lots of open porosity. Fluids flow quickly through it. A low permeability medium is one with small pores, and therefore very slow flow, that you have to apply a big pressure gradient to suck fluid out of it, which is why you hydraulically frack shales, because they have no natural porosity, very low natural porosity. So you have to put permeable conduits in them. And so you just do this at the wellhead. You never do the physical test, but you do a digital test to be able to look at this. And I guess the red to blue coloration is between high pressure upstream and low pressure downstream. And these are blobs of a fluid, a liquid, perhaps with a gas around it or something, with two phases in it. It's much more complex than anything we'll do in this class, but that's one kind of application of some of this. So I don't know what that will do in the background. I guess perhaps I should close it down. Oh, perhaps it just continues. And these are kind of some interesting ones as well. So that's for porous media, but also the things that we've been talking about, things in the air where there's no porous medium surrounding it. And these are, again, just models that would track individual blobs of water a packet of water as it comes out of this imaginary hose that's filling up this bucket. And it would be using conservation of mass and conservation of momentum. So these droplets would be falling just at the same rate as if you're dropping a pen due to gravity. That's really what fluid conforms to. It doesn't care if it's in a fluid on its own or in a cup a beaker that you're dropping that contains it. And so there's relatively sophisticated models that can do these things. And of course, these are, again, just, so we won't certainly talk about these things, but that's what the background that we're talking about today. Certainly, if we get to it today, we'll talk about using porous media flows, because that's perhaps relevant to many of the things that you're doing. And the final one, I think, is kind of curious as well. I think it's a longer one. I think it's the final one. What's this? Oh, yeah, not the final one. These are quite interesting. A whole bunch of things. I'm not sure we'll look at all 3 minutes, 51 seconds. But again, the same for these open flows that we could, which are really just by using this conservation momentum equation, which was last week, right, week 7, with energy losses in it, which is kind of this week, but we don't really cover it in this course. And so you can look at interaction of solid blocks and fluids. I think behind this, there's a big compute engine which is doing this. And in one of the videos that comes up, you'll see the kind of idea of the model. I guess these are all chapters. This is, yeah, so you can see this. So this is a cut through it, and this on the right, you see this grid. So each of these grid blocks would be a little square conservation volume, what we've called our control volume, that fluid comes into it on one side, accumulates or goes through it on the other side. The grid in this case grows to accommodate the fact that the geometry of the flow is changing. And so the compute part is on the right-hand side, and draped on the left-hand side would be some kind of rendering. So these are used this is what they call it in movie making. So these are computational imaging which is used in movie making. And same idea for flow of water down a slope. You can see on the left this kind of growing grid. The gray part is just all these little squares that allow you to do the conservation equation. They kind of multiply and grow as the upper surface of the flow changes to be able to accommodate that. And obviously there's a fancy rendering that's put on top of that to be able to use this for computer graphics, to be used in movies. And so a lot of the special effects you see these days, certainly not for the Poseidon Adventure, right? If you remember the Poseidon Adventure from the first time we talked, the model liner being hit by the tsunami, I don't think that was computer-generated graphics. But now this is done this way. And this is, again, another kind of cool model of waves breaking over a lighthouse, etc. So all done by modeling. So some of the techniques that we've kind of alluded to. We won't certainly go into any of this, but you can see maybe the potential for some of the things that we've done here already. I think that's it. I don't think anything else exciting happens then. But quite sophisticated to do this. And NVIDIA, I guess, is involved in this because these the compute engines for these things are put on GPUs, graphical processing units, which are for games, which can compute things much more quickly than regular chips, I guess. So that's it. So what will we do today? Well, today let's briefly review what we talked about last time. There's these two individual expressions that we talked about, and just reiterate the background behind those. Maybe do a couple of examples, and then maybe look at, I guess the last of the ones I didn't show on this, he says. And so something much closer to home for some of you would be something like this. And I don't know where we are in this model. Yeah, so if you want to model the extracting gas from the subsurface, or how far a plume of contaminants travels in a given time, then you typically use models which would be like this. You have your aquifer in plan view. You divide it up into a whole bunch of little grid cells. Each of these grid cells are just like our control volumes that we look at. Mass rate in equals mass rate out, and the difference between those is what accumulates in that cell. And you apply some boundary conditions on it. Maybe you have some surface water sources going into your aquifer by these rivers here, and you put some boundary conditions on it, and you use it to project what the outcome is in terms of where the plume is after a year or 10 years, and what happens if you put some wells in to suck some of the stuff out of it. And the same for looking at petroleum reservoirs or geothermal reservoirs, depending on your proclivity, or flow into underground mines, for instance, or flow around tailings dams, to cover all of these 4 programs that exist in this department, and I presume in this course as well. So that's that. So to do this, these all require, I mean, the reason that we're talking about these things now, not maybe 2 weeks ago when we were talking about conservation of mass, is that all of those systems rely on some loss of energy. And I guess I should do this. And yeah, okay. And so this is the first week we've started talking about losses. We talked about 2 equations, and we named them 1 and 2 last time when we went through them. I'm not sure we have to spend too much time on them, but to mention that we had an energy equation which allows us to take care of Bernoulli. It's written between it's along a streamline, just as it was for Bernoulli before. And it's important that we write things in terms of upstream and downstream, as we have here, in the right way around, but also this would be out and this would be in, and so on, in the same way. So in terms of Bernoulli, we've got these 2 equations, which are the velocity head and the elevation head, and we also have this enthalpy term, which is equal to the internal energy per unit mass plus pressure over density. And surprisingly, no big deal, just quiet. So not surprisingly that these are in terms of joules per kilogram. In terms of energy, joules is Newton meters. And I guess surprisingly is that these terms, which are in meters squared per second squared, if you multiply by kilograms, both top and bottom, we did this last time, then this comes out to be kilogram meters per second squared per kilogram. So this term here is plus an extra meter, right? So this term here, kilogram meter per second squared, is a Newton, times a meter is a Newton meter, which is a joule, and divided by a kilogram. So it's all surprising that we are adding apples to apples. They just don't look like apples and apples. But so that's important to know. And I guess the other thing is that these would be in joules per kilogram. So mass flow rates would be in kilograms per second. So the product of kilograms per second and joules per kilogram is in units of joules per second, running out of space, which is a watt with 2 T's by definition. So it's quite neat the way they work out. I guess the other thing is we didn't really use this in a thermo mode, but there's also an equivalence between work, described as positive if you're putting work into the system, which would be a pump, and negative if you're taking energy out of the system, which would be a turbine, and also thermal energy. So I guess there's a correspondence between thermal energy, and I can't remember what it is. Is it a joule is equal to 4.2 calories, something like that? I don't quote me on that, but there's an equivalence between thermal energy and mechanical work. And you can look it up on Google as to what it is. And so there's an equivalence between these things. So these would work out to be the same units in this. So that was for the energy equation, where we have thermal energy going into it in terms of enthalpy into a turbine. The second one, which we'll use much more often, we did all the use we'll do with this one last time, is written properly this time in terms of upstream to downstream. I don't know whether I'm able to do this. Let's see. If I go back to what we did last time, we avoided lots of math. I'm glad we did that. This is what I'm after. See if I can be skilled and do this. I'm not sure whether I can. Is it copy? Is it going to copy it? See if it works. If not, I'll just draw it from scratch, because I think it's a useful figure to have. Oh, man. Look at that. You'll want to hoist me on your shoulders. All right. So, yeah. So we'll go back to what we were talking about. So this equation is written between upstream and downstream, always. And the reason is that the pump head is on the left-hand side and the head losses are on the right-hand side. So it absolutely has to be written between upstream and downstream. And so if you look at what that might look like, then this energy equation is kind of explaining what it is, or this little diagram here is explaining what it is. And so if you have a datum that sits here, you have a pipe, which is, again, this is along a streamline. It's kind of a one-dimensional representation of our system. Upstream velocity, upstream pressure, upstream elevation, obviously, and the same downstream. And so the way to think about them is that these terms on the right-hand side are the elevation head, the pressure head that's added on top of this, and the velocity head on top of that. And on top of that is some energy you might put into the system as a pump head. And as it flows along here, as the fluid flows along here, there are these frictional losses along the side of the wall. And it's these frictional losses that eat up the head. And for now, we can think of them as this term here. This is consistent because the units of this have to be in units of length. So the units of this head loss also have to be in units of length. We know that v squared over 2g is already in units of length because it occurs in this equation. So this has to be a non-dimensional coefficient. It has no units. And the other thing that we'll use a lot is that the pump head is equal to the power in watts, the rate of doing work, divided by what we've called uppercase M, the mass flow rate, times G, which we could also get away with calling power divided by volumetric flow rate, Q, we've often called it, density. These together are the mass flow rate, right? And gravity. But again, this is in units of length, which is convenient. And so that's the one thing you have to be aware of, that you can write this. This is kind of a modified Bernoulli with energy losses intrinsic in it. This is the energy grade line. If you remember, this HGL is the hydraulic grade line, which is just the sum of elevation plus pressure heads, which is used in porous media flows, which we'll use maybe later on today, or on Friday. And I guess you could also think about this, it's probably worth spending a bit of time on this figure, is that if you remove these parts, which I can do, I'm not sure if you can do in your notes, then you could imagine that in reality, if we don't have any pump head in the system, we said last time that the essence of what these flows in a pipe are that you have flow along a pipe. I could just pull it out of our notes from last time, but I'll do this as well. If you think about it, then this is the area. This is P1, which is upstream. This is P2 that's downstream. It has a velocity that's flowing at V2, etc. But we're not interested in the velocities. We know if the pipe's the same diameter or cross-sectional area, the velocities upstream and downstream have to be the same. So V1 equals V2. But we know that the difference between P1 minus P2 multiplied by the area has to equal this shear stress, tau, applied over the length of this. So this was pi d times L. Is it flu season already? You're from Fumar? This is shear stress times pi dl, which is just the area inside the thing. And this is pi d squared upon 4. And so if the shear stress is finite, then by definition, there has to be a difference between these. Pressures can't be the same as you go downstream. So in Bernoulli, this was always the case, that these heights of the pressure heads, upstream and downstream, had to be unchanged if the energy grade line was constant. But in the case where we're losing energy along the pipe, then I guess we could redraw this. If I want to be careful with my colors here. So this would be, by definition, shorter. I won't rearrange these. By definition, if the velocity upstream and the velocity downstream are the same, because the areas are the same, then that doesn't change. So this line has to go across here. And so this difference here has to be the only term that can fit into here, which is the head loss. So this is the better way to draw this, or another way to draw it, would be with the datum, with the Z1, with this would be P1 over gamma. This would be P2 over gamma. This would be V squared. Not too well. And it would be parallel, right? This would be V1 squared over 2G. And this would be V2 squared over 2G. And the top part would be, this is the flat energy grade line, and this amount here would be HL. So, and this, I guess, would be our tube along here. So it's exactly the same as the figure above. It's just we've switched HL and V squared. Just to honor the fact that the V squared term has to be parallel to the drop in pressure. And so that's really what this expression means. And if we wanted to, we could add head into it as a pump head. Okay? All right. So let's use that. I was going to do I was going to do it a bit differently this time. Let's see if I can do this properly, as opposed to improperly. No, that's not it. Is that it? See if it works. 2 victories and 1 more, and I don't know if I'm ready for that. Oh my God. I don't know if I want. You can see that reasonably well? Yeah, I want to keep them on the same page at the same time. So, I mean, we could go, you have these solutions that are just from a solution manual that show you how to do these things, but it's probably better just to talk about how we'd approach this in terms of how to solve it. And so let's do that instead today. So pump transfer water from one large reservoir to another. This is the lower reservoir, it's kind of pump storage, I guess you could think of it, into the upper reservoir. Keyword, right? You know what this keyword means. Large means that the velocities here are 0, if you choose to write it there. Difference in elevation, well, it's in English units. No, let's not worry about that. The frictional head loss in the piping is given as this magnitude. So this value is what we've called H sub L. And importantly, it's written in terms of the average velocity squared. So it'd be the velocity not in the reservoirs, but in the pumps. So this would be V average going along here, where V is the average velocity in the pipe. KL is the loss coefficient, which we don't know, I don't think. Relation between the total head rise across the pump and the flow rate through the pump is given in this figure, which means if you want to pump quickly, you have to provide a lot of energy to it. The pump head is high. If you want to pump only slowly, then you don't have to provide very much pump head energy to the system. Remember that pump head is equal to the rating of the pump in watts, if you like, divided by mass flow density times volumetric flow rate times G. And so you have that. We know the value of this loss term, which we have, and so we want to know exactly how to solve it. And so I'm going to write the equation. I know it's written there, but I'm going to write it again just because I can. Remember, we write from upstream to downstream. Well, actually, I don't need to. It's written out before. Why don't I don't. So what do we know? Well, we could choose any point to start off, but we need to choose a point where we know things. I guess we'd know here that P1 is equal to atmospheric. So if you work in gauge pressures, that's 0. We know that V1 is equal to 0. We know that here that P2 is atmospheric and that V2 is equal to 0. And so immediately we've got rid of a bunch of terms here. So these are all zeros. So I suppose Z1 and Z2 aren't the same, but we have to go from upstream to downstream. We know what each of those are. The difference is 100 feet. I guess we've got to keep the sign convention. What else do we know? I guess we have an equation for pump head, which is equal to this, which is defined in terms of this equation. So I guess we could write this as 2 minus Q times 100. So in other words, when Q is equal to 0, then 2 times 100 gives you pump head is 200 feet. When Q is equal to 2, 2 minus 2 is 0, the pump head is equal to 0. So this is just the equation of a straight line. So this is the pump head. And the head loss is going to be equal to KL times V average squared over 2G. And I guess we know that this is equal to 20. So, if we wrote it out with the things that we know and don't know, I guess we have z1 minus z2 is equal to wrong things. This would be term plus HP equals HL. And so Z1 minus Z2 is equal to, I guess, minus 100, right? HP is equal to 2 minus Q times 100. And HL is equal to 20 times V squared over 2G. And so we need to know that, do we have a diameter for the pipe, for the average flow rate? Diameter, yeah, we do. So we have one equation, we have two unknowns in that equation, so we have to marry them in some way. So we have to link these two velocities. And so we link these two velocities by noting that Q is equal to V bar times pi d squared upon 4, which is just equal to the velocity times the area. And so we can write this in terms of Q, or we can write this alternatively, that Q is equal to V bar times A. And so we have an equation that's written only in terms of V bar squared and V bar, and everything else we know. And so we can solve it. And so you can see in the solution, I think it's easier doing that than going through the solution. They do exactly that. They write Bernoulli's equation to get rid of the terms you don't need. You only have the pump head and the head loss, plus the elevation changes you know. You have the pump head and the head loss. You write the volumetric flow rate in the pump head in terms of the average velocity in the pipe. And if you do that, you can write the head loss in terms of that volumetric flow rate. And then you get a horrible equation to solve, which is a quadratic, more than we need to do here. But that's basically how you set the problem up. So I think a lot of this course is grasping exactly how to set these problems up. So that's it. So you can have a look at that at your leisure, and you'll certainly find it worked through ad nauseum in previous years' videos as well. So you can do that. Let's try my newfound skills again. To cut this out. Again, just go through the skeleton of how we do it. You have some space, I think. Yeah, good. Oh, it's even got the key on the side. That's interesting. All right. So again, another energy loss question. So you have water coming in through here. It's not water, it's gasoline, I guess. And it's the specific gravity is 0.68 of that of water. So that means that the density of the gasoline is equal to 0.68 times density of water, which also means that the unit weight of gasoline is equal to 0.68 times the unit weight of water. So 680 kilograms per cubic meter. Goes through a pump at a volumetric flow rate. So this is a Q. So we know what the Q is through here. Head loss is given equal to 0.3 times the velocity squared at location 1. So you know the velocity 1. You know, we don't know the velocity 2, but we have a flow rate. And it's a bit tricky because they're different cross-sectional areas. And the question is, what's the difference in pressures between P1 and P2 in the system? So we write Bernoulli's equation between the upstream and downstream, have to. Even though it's going uphill because it's being powered by a pump, but this is upstream and downstream. And so I guess we work with Bernoulli. So we don't know what the pressure is. I guess that's the object, what we want. We can't now assume that the velocities upstream and downstream are the same because the cross-sectional areas are different. The diameters are different. But we can link those because we have flow rates. So I guess we could write that V1 is equal to Q divided by area 1. And we could write that V2 is equal to Q divided by area 2. So that allows us to link these two terms here. So that's, maybe we have these terms. And we have the elevation difference. We have Z1 and we have Z2. I don't like writing it this way. This is just HP. I'm following the solution. I don't like it. That's not 1 over HP, it's HP. Pump head. Right? These are all in units of length. This is in units of length. This is in units of length. And we know that HP is equal to W dot rho Q times G. We know that this is equal to 20 times 10 to the 3. Ten to the 3 watts, which is Newton meter per second. So we just have to use SI units and everything should work out okay. So I guess we could rewrite that equation in terms of what we want. You want to get the head loss between section 1 and 2, which will be the pressure difference, right? So you could write this as P1 minus P2 over unit weight of gasoline. And that's going to be equal to Z2 minus Z1. I'm sure I'm going to leave out terms. Minus rho QG. And we can't get rid of the v squared terms. It's going to be minus 1 over 2g v1 squared minus v2 squared, right? This is a positive term, stays positive with this minus sign. And am I missing anything? I don't think so, right? I probably am. Missing a few gray cells, I'm sure. And so these, now we can write these in terms of this in terms of this, and this is in terms of volumetric flow rate. We know that the difference between this is 3 meters. This is plus 3 meters. We know what the specific unit weight of this is equal to 6.8 kilonewtons per, this is going to be about 6.8 kilonewtons per meter cubed, because water is 10 kilonewtons per meter cubed, or 10 to the 4, I guess. 6.8 times 10 to the 3 instead of kilonewtons. And then I think we have everything to solve this. This is 20 times 10 to the 3 watts. Just this. And it's all in the right units if we're doing it that way. And again, it comes out to be a horrible solution, I think. I'm not sure. You can see the stuff here. I think they do it a little differently. They use pressures instead of pressure heads. I think it's always easier to use pressure heads myself. But they do exactly the same. They write Bernoulli between upstream and downstream in the right way. They get velocities in terms of volumetric flow rates, both here and here. You can link the velocities V1 by the ratio of the areas. It's just the same as what we did in defining the flow rates in terms of this. It's exactly the same. And then when you solve it, you get a horrible solution with, well, you know most of the terms. It's just a bit cumbersome because you have to substitute for flow rates. And you get a pressure drop between those two upstream places. But the deal is that perhaps seeing it in this form, you have everything you need to know on the right-hand side in terms of volumetric flow rates. And you have a volumetric flow rate, which is this magnitude here. So immediately you know what velocity is, you know what this velocity is, so I guess it's not that cumbersome. So, yeah.
I think you're missing your head loss there in the equation.
Oh, yes. Thank you very much.
I think they just give that to you.
Yeah. So this is in terms of V1 squared over 2G. Yeah, I am. So this term here is this term here, right? It's in terms of a velocity. And of course, the velocity here, this is 0.1 of a meter, this is 0.2 of a meter, so this velocity will be faster. V1 is greater than V2 because these cross-sectional areas. And so you have this velocity defined in terms of a volumetric flow rate, thank you, and you can solve. So that's it. So, okay, fine. All right, what else do you want to talk about? Well, maybe those are the only problems I was going to work through. The other stuff after that wasn't. We went through a dam one the other day to talk about the relative losses between going upstream and downstream. What's this? I don't want to talk about that. Yeah, I will. So rounding out what we've talked about, perhaps I can do a quick exposition of this. So flow in porous media. And so the last figure we looked at in the movies, this plan view of a grid for flow, is kind of how we might be able to look at taking a piece of porous media, porous medium, which is this, and if we look at conservation of mass, if we go back to that, you'll remember that our definition of that was that density times changes in volume, rates of change in volume, plus volume times rates of change of density, plus sum of mass flow rates equals 0. And so this flow in porous media is a pretend conservation of energy problem. And I say pretend because we get it through conservation of mass. We only solve conservation of mass. So if you remember this system from before, we had velocities in terms of our system. How am I going to do this? Yeah. Velocity, no, that's velocity. This is velocity v plus dv dx, which we can multiply by dx dx. And we can have a system of coordinates, a right-handed system of coordinates. So this, I'll call this, I guess I should call it y. And so let me change this to y. And rewrite that. So this is y, this is y, and this is y. This is dx, this is dy, and this is dz. And if we write out this expression here, let's ignore the accumulation terms, then sum of the mass terms is going to be equal to density times area times V upstream plus density times area times V downstream. Right? Minus sign because flow rates in are negative, and by definition. So if we write this as density, the cross-sectional area is dx dz. And then we can write these other terms here. This is V upstream. Let's just call it V. This is V plus dv dy dy. This term is negative, and so these two terms cancel out, and we're just left with a mass flow rate which is equal to density times dx times dz times dy multiplied by change in velocity in the y direction. These terms together are just the volume of this cube. And this has to equal 0. So this is just a statement of conservation of volume, conservation of mass, which is conservation of volume. And so we could do this in the x direction. In the y, did it in the y direction. We can also do exactly the same for flow in the x direction, which will be out through here. And we can also do it for flows in the z direction. And it won't come of too much of a surprise that the sum of mass flow rates are equal to density, volume, dvx dx plus dvy dy plus dvz dz. So that's a conservation equation. It doesn't say anything about energy losses within the system. So what Henri Darcy did in the fountains of Dijon, he took a piece of core, not sure he did this actually, and he did a little experiment to be able to flow along this core of some length and some, well, let's not worry about the area, some velocity of flow. And he made that velocity of flow occur by having a an elevation of this core, Z2 and Z1, right, to get our directions right. And he had a pressure change on the core between P1 and P2. And his little experiment allowed him to say that when you do this experiment, you find out that the velocity of flow as it comes out of the end is equal to proportional to the pressure change, in this particular case, along the length of it. Let's do this as the x direction. And multiplied by a term which is this. This is the permeability. And this is the viscosity of the fluid that's flowing. So this is the viscosity of water. And so what you can do, since we know this expression for steady state is equal to 0, you can write this term as dvx dx equals 0. You can take this and plunk it in here. I guess that didn't work out. And you end up with k over mu d2p dx squared equals 0. One component. And so this is just the way of getting the equations of porous media flow, which you'll use to represent groundwater flow. We'll actually use them on Friday to do a little simple flow net problem. Do environmental systems engineers take GSci 452 now? Yeah, you've seen some of this. If you haven't seen it, you'll see it. So this is just where this expression comes from. And so the reason for doing it here is that this point here is it's a pretend energy balance problem. All we've done is solved conservation of mass. Mass rate in equals mass rate out. It says nothing about energy loss. It's not the Bernoulli equation that we've dealt with. But the loss equation is that this is just like our pipe equation. There's some frictional loss within the core. It's not on the walls of a tube, but it's flowing within the interstices of the core, just like we had, if you're not St. Martin, if you saw this, just like in this. In flowing through this core, if you take this core as being filling up this pipe, there's some drag on all this fluid which you're amalgamating and representing it by this loss. And as we said before, the fact that we have pressures which are lower downstream than upstream mean there's some energy loss. So we're representing this energy loss just through this coefficient here, permeability. We can also write this equation for ground. This is for petroleum engineers. We can also write it as hydraulic conductivity times loss of head with distance, where a hydraulic head is just the sum of elevation plus pressure head plus this set as 0. Velocities are so small, and changes in velocity are so small in porous media flows, we don't have to worry about it. So these expressions are kind of equivalent to us. They have a minus sign ahead of them, actually. The minus sign is because the positive x-axis is in this direction. This is a positive gradient in pressure, dp dx. The flow that it elicits is in the negative v direction. This is positive x, and it's going the other way. And so there's a minus sign ahead of this. Don't care about the minus sign in this. And so this is where they come from. So that's just an exposition of that. Amazing, don't you think? Oh, he is so smart. Okay, that's it. So we'll build on that next time. We will use we'll talk about a technique called flow nets, where we can use this steady state porous media flow to be able to draw some pictures of what the flow should look like, and get very accurate estimates of flow rates through them, through structures, which are quite useful. And this is the final part that builds on it. So we'll talk about that for the last time. Yeah, that's it. Great. Good seeing you all. Any questions? Of course not. Okay. Thank you.